Welcome to example 2-12, pressure on a plug. So you can see we have a water container that has a slot at the bottom, and then there's a half cylinder that sits in that slot as a plug. And of course it continues on into the page, so it says that the length of this is 0.5 meters. All right, so what do we see? Well, if we look at this, of course we notice that if you're looking for the vertical component here, right, because they're asking what the normal forces are going to be here and here, then we can say, well, we know that we'll have a vertical force from the water, and that's just going to be vertically downward based on all of this, right? That whole chunk of water, that weight of water is going to push down, so we can use that. The other thing that we know is that, of course, we have on these side pieces here, we'll also have water pressure acting on that, and it will push upward, right? So we'll have to find out what this volume looks like as well, right? Because that will be our pushing upward. Let's look at these at a little more detail. So let's do a sketch over here. This would be for our vertical downward force. That's kind of easy, right? That's just the weight of water sitting on top of it. All right, that'll be that piece right there. So we know that length there is 0.6 meters. We know that it's 1.5 meters high. But that's given as our H. So it's going to be easy to calculate what our volume 1 is. Now for the second one, it's a little more difficult. Let's draw this a little bigger this time. Like that. Right, we're trying to find these slices here. So let's maybe draw in what we have, right? So we'll have this contact point would be here. Maybe this is where our center is. Right, so we know that this line there has to be 0.3. We also know if we do a dashed line down here, length of that line has to be half of 0.45, right? So this we know is 0.225 meters, right? 1/2 of 45 centimeters. What else do we want to see? Well, we in the end, right, we'll want to find out what this little pizza slice is here, right? To know that, we'll need to know what this angle is. All right, what is that angle? Well, that angle is the same as this angle. We'll call that alpha. And so we can say that alpha, right, in our case, we know what this length is and we know what that length is. So we can say cosine alpha is then going to be 0.225 meters divided by 0.3 meters. Based on that, we can say alpha is equal to 41.401 degrees. All right, so that's good. So we have that slice. Now we don't want to have this entire slice, right? All we want to have is, maybe we'll do it in blue, right? We want to have this part here of the slice, and then of course we want that to continue on top. Right, so this is what we want. So if we want to have just this area in here, right, that's what we'll need. So that's going to be the entire slice minus, we'll do it in red here, right, minus this red triangle. All right, so maybe we'll just write these out here. Let's see what we can get. So if we want to get the volume, let's call this volume 2. Volume 1, we don't really have to calculate. That's easy. But if we want to do volume 2, I'm sorry. All right, then what do we have? Well, we know it is going to be 0.5 meters in length, so we can put that in front. And now what do we have? Well, we have the first piece up here, right? The chunk on top. Maybe we can add another thing here. Of course, we know if the bottom part here is 0.225, then up here this is going to be 0.3 minus 0.225 meters equal to 0.075 meters. All right, so we know that this chunk on top here is going to be 1.5 meters times 0.075 meters. That's the big one up here. And then we can add that entire slice, right? This entire slice is just going to be a full circle, right? You know, the entire thing divided into that little piece, right? So we can say that'd be pi r squared. So pi times 0.3 meters squared. And then we just want that one piece, so 41.401 degrees over 360 degrees, right? That goes from an entire circle to a slice. And then we just subtract our little red triangle here, right? So we can say that would be minus 1/2. It's a triangle. We know that one part here, that part is 0.255 meters. And then this height here, right, we know what the length is here, so we can know that it would be just 0.3 meters times sine of 41.401 degrees, right? Because we're looking at trying to find this length, and we have our angle up here, and that's the hypotenuse, so we'll get all that. All right. So let's make sure we got everything, right? So we got the top part up here. That's our first set. Then we're saying we're going to take the entire circle. That would be pi times r squared. But we only want to have a chunk of the circle, right? That's why we're taking out that section. And then from that section, from that pi slice, you need to take out this other triangle. So now we're left with that. So I think we have everything there. So from that, we can say, if we plug in the numbers, we get something like 0.061348 meters cubed. So that'd be our volume 2. Our volume 1, just so we have it, real easy, right? That's just going to be 0.6 meters times 1.5 meters. And then the depth into the paper, 0.5 meters. And that then leaves us with 0.45 meters cubed. Makes sense, right? That is going to be much bigger than this one, so that at least looks reasonable. All right, so then if we want to find what the vertical force in total is, right? Our total vertical force, right? That's going to be gamma times the volume of water. Now in our case, we have one part where the pressure is going to be, the force is going to be acting downward, right? Because that's where the water's sitting on. On this one, it's pointing upward, right? So we can just subtract that. So we can say this would be volume 1 minus 2 times volume 2, right? Because of course we'd have this on the other side as well, right? We have that same little thing over here, right? So we have 2 of those, so we have to subtract 2 of them, and then we can plug that in. So gamma is 9,810 Newton per cubic meters. Volume 1 was 0.45 meters cubed minus 2 times 0.061348 meters cubed. And then if we put that in the calculator, we get 3,210.8 newtons, or 3.21 kilonewton. And now if we want to find what our normal force down here would be, right? I'm split up between these two, but if we just take it together as one big normal force, right, we can just do sum of forces in the vertical direction. Already have FV, so let's say Fy equal to 0. And that would be my overall FV would be acting downward, right? Because most of the pressure is going down, just a little bit up, minus the weight of our plug there, and the N that we want to find. So we can say N would be FV plus W. FV we just said was 3,210.8 newtons. And then the W, what do we have there? I'll write that on the next line because I think that might be a little longer. So that would be plus, and then so we have a half cylinder. So let's do area of a cylinder and then a half. So let's do 1/2 times the volume of the cylinder. So that would be pi r squared times, in our case, the length, right, goes down 0.5. And then, of course, we still need to change our density here. So that would be then times rho times g. So that would be 3,210.8 Newton plus 1/2 times pi 0.8 meters squared, 0.5 meters, times the density was 7,850 kilograms per cubic meters times 9.8 meter per second squared. That's already newtons, so that's good. This one's going to be cubic meters, so cubic meters cancel out, and we have that, yes. So we get something that looks like newtons. And so we are left with 8,654.257. Or 8.65 kilonewton. So that's going to be the normal force that is acting on the bottom of this, the kind of where the plug sits on these on the sides. Now this is for the entire length of 0.5 meters. So we could spread that out as a distributed loading. All right, but with that, figured out how to calculate the pressure on these kind of interesting shapes, and we found that it would be 8.65 kilonewton.